This is the second calculus lesson. It is on a new topic, related rates. As we all know, derivatives are rates, speeds of a sort, how one variable changes as a function of another. So we're going to go over quickly what we understand about derivatives before we go into a definition of related rates. So first, we start with what we started with in class, which is just simple explicit functions of one variable, like this line, y equals 2x plus 1. And its derivative is its slope, and it's telling us that every time x goes up by 1, y goes up by 2. And here's another explicit function of one variable. It's just one you like a little less. Y is the natural log of x, and its derivative is 1 over x. And this third example is here just because we have to always remind ourselves that it doesn't matter which symbols we use. We can still have an explicit function s of a dependent variable, of an independent variable t. And this should remind you of position being a function of time. And in this case, ds dt is 2t. After we did the simple functions, we went on to look at combinations of functions. So we have products of two functions, quotients of two functions, and compositions of two functions. But in every one of these cases, the independent variable or function is a function of one variable, an explicit function of one variable. We departed from that when we first went into the topic of implicit differentiation. In implicit differentiation, we do not have an explicit function. We have a function, y perhaps, that seems to have equal status in the equation with x. And we can take the derivative if we know we're supposed to get dy dx. Then the derivative of x squared is 2x because it's the derivative with respect to x. And the derivative of y squared becomes a chain rule problem. Y is a function of x. So 2 times the function, 2y, dy dx. And the derivative of 25 equals 0. And then, like we have in many implicit differentiation problems, we actually have to solve for dy dx. So we subtract 2x from both sides, divide by 2y, and the derivative is negative x over y. The two ideas that were introduced with implicit differentiation is that we can have functions anywhere in the equation. We can take the derivative with respect to any variable, and then we can solve for the derivative that we want. So when we start related rates, the first thing to realize is that we're only making a small addition to what we have already been doing. We've already recognized that y can be a function of x and u and v. And if I ask you to find dy dx, you suddenly know that everything is a function of x, and you take the derivative with respect to x of everything. We separate that. The derivative of x with respect to x is 1, but then we just have du dx plus dv dx. Remember, when we just have a symbol, we have to make assumptions about what it is, and the derivative we're asked to find with a problem context tells us the kind of assumptions we make. And we don't know what u and v are, but we have symbols for the derivative of u with respect to x and the derivative of v with respect to x. And similarly, we could decide to take the derivative. Let's bring this down just a little bit. And let's say instead of dy dx, we want dy dv. dy dv. So now we're assuming everything's a function of v. So x must be a function of v, and u must be a function of v, and well, v is an obvious function of v, and its derivative is 1. It's this change in the variable that matters that is the first thing we're going to think about with related rates. Because related rates are really about speeds, relative speeds. And so we're always going to be talking about derivatives with respect to time, just like we did when we were doing motion. So starting with this example, we can, even though time doesn't show up in this equation, we can look at the derivative of y with respect to time. Then everybody's a function of time. dy dt equals dx dt plus du dt plus dv dt. That, in its most simple form, is the story of related rates. We look at one derivative, one rate, as a function of other derivatives, another rate. So let's consider this in a slightly more interesting example. Suppose we have x squared plus y squared equals 25, just like we did when we knew that we only wanted dy dx. But now I want dy dt. Because think about it, x and y, as they're moving around this circle, remember this is the equation of a circle with a radius of 5. So think of x and y going around the circle, and they could go at different speeds. But those speeds must be related, because x and y are just points on the circle. So you could actually think of it as an equation relating to some kind of arcade game. So let's take the derivative with respect to time. And now x is a function of time, and y is a function of time. So we're going to use chain rule. 2x dx dt plus 2y dy dt. I have to write this correctly. Equals 0. And I can solve for dy dt. I subtract 2x dx dt from both sides, and I get 2y dy dt equals negative 2x dx dt. We get a little more space so we can finish this. And dy dt is negative 2x divided by 2y dx dt, or negative x over y dx dt. This is our first related rate problem. We had to figure out how y was changing as a function of how x changed. And remember when we were just looking at dy dx, the derivative was just negative x over y. So it's kind of nice to see that that's part of the derivative when we do related rates. It's really not all that different. And derivatives are rates. So it's shouldn't be all that unfamiliar an idea anyway. So let's do one real related rates problem. Let's think about a circle. So I have to freeze my screen to get a circle. And this tool should make a circle for me, although I'm not sure it actually will. And my circle has a radius. And you know that the circumference of a circle is 2 pi, pi is a number, remember, times the radius. And in this situation, I have a circular puddle, and the radius is growing. It's raining. The radius is growing, and so it has a rate of 1 meter per week. The radius is growing slowly. It's been a rainy week, though. I want to find how fast is the circumference growing? What's its speed? So I take the derivative with respect to time of my circumference equation. And this is the first important idea here. If you're going to find one rate in terms of another rate, you need an equation that relates the two functions, relates the circumference function to the radius function. If dr dt is related to dc dt, r must be related to c. So dc dt equals 2 pi, since that's a number, dr dt. And since dr dt is 1 meter a week, we can substitute dc dt. I'm going to just move this up a little bit. Equals 2 pi times 1 meters per week. Notice that 2 pi is much bigger than 1. Pi is approximately 3.14159. So twice that is much more than 1. The circumference is growing much faster than the radius. Congratulations! You have solved your first related rate problem.